If I say musician, what's the first thing that pops into your mind? Maybe a guitarist strumming his strings, or perhaps a conductor
Guiding.
orchestra to a crescendo. What you probably didn't imagine is a music theorist at
Her.
desk with a pen and paper sketching out graphs. Usually people don't really think of math and arts mixed, but there's quite a lot of math baked into music. For example, the reason some intervals, like this, sound better than others is partly due to how simple their fractions are. This is a cool tidbit for sure, but are there any other ways that numbers pop up in sounds? Turns out, numbers show up in music all the time in other surprising ways. For example, like graph.
In music, a note is a sine wave at a set frequency that we hear as sound. For example, is a note. Since musicians are quirky, notes correspond to one of the 12 note names: C, C sharp, D, D sharp, E, F, F sharp, G, G sharp, A sharp, B, and C. Most music uses about 7 of the 12 notes in the octave, called a key. There are many kinds of keys, but we'll focus on the two most common: major, happy, and minor, sad. For example, this is D major, and this is D minor. In every major and minor key, there are different kinds of chords. A chord is a collection of 3 or more notes played at the same time with a certain quality. We'll focus on major, minor, and diminished chords. All of these chords have 3 notes, and you can switch around the order. For example, F major. These are all called inversions. When you have a sequence of chords, you need to think about how inversions could have good voice leadings, which is how each chord transitions to the next one. Some voice leadings sound jarring, while others flow better. The big idea we're trying to explore here is which voice leadings to use for the best results.
Now we have our question. Given a sequence of chords, what's the smoothest voice leading between them? Here's how we can use graph theory to help. Brace yourself for another crash course. A graph is composed of vertices, also called nodes, and edges that represent relationships between them. Graph theory pops up everywhere in the real world. There's a graph showing job employers with edges representing a good relationship. How do I network from employer to employer by talking to the least number of people possible? This example requires a path, a sequence of connected vertices. Edges can have weights, like toll costs, which change the path you pick. In our problem, we can represent all chords in a key as nodes. M is for minor, dim is for diminished, and if there is nothing to the note, it's major. We also represent its inversion as 0, 1, 2. Edges represent a transition between two chords. Let's say you wanted to find the shortest smooth path between two faraway chords. This means you want to minimize cost and the number of vertices in your path. To do this, we used a musically informed Python script that implements Dijkstra's algorithm to find the lowest cost path and sort it by length. You put in your start chord, end chord, and cost tolerance, and it outputs the top paths to get there. How inspiring. Here are a few progressions from the script.
This is very inspiring, but does anyone care? It would be cool to see if we can compare real songs and our algorithm to see how close of a fit there is.
Une mémoire d'écrire mon histoire à l'encre bleue. Laissez-moi construire, laissez-moi, laissez-moi danser, chanter en liberté tout l'été. Une mémoire d'écrire mon histoire à l'encre bleue. Laissez-moi construire, laissez-moi.
It seems our program closely matches the artist's intentions, with a few minor deviations. Thank you so much for watching, and we hope this video taught you a lot about graph theory and music theory.